So first let's talk about what a monomial is. So a monomial is a number, a variable, or it's the product of those two. Okay? What? Okay. So the blanks you should be able to be filling out in your notes. Alright, some examples that we have down here, just like the definition. A monomial is a number. So right here, 80 would be an example of that. It can be just a variable, so it can be just X or Y or Z, something like that. Or it's the product of the number or variables. So right here we have the product of a number and a variable. Okay. It could also be the product of two variables. It could also be X, Y. Okay. So I also gave you some examples of what are not monomials. So somebody tell me why both of these look like they aren't. What's different about those than these? What's different right here? All right, Jack.
Well, they aren't multiplication.
Yeah, they're not multiplying. They're doing what, Ethan? Adding and subtracting, right? So we're adding and subtracting, so that makes them not monomials. Well, but by themselves is x1, is 5(1), x squared, right? Because that we could represent that as the product of x times x, and y squared is 1. But when we're adding and subtracting them, that does not make that whole unit a monomial. All right, has everybody got that written down? Okay. All right, so now let's talk about what we do when we multiply monomials. So when we multiply powers, keyword here, with the same base, we do that by adding their exponents. Okay. So in symbols, if we have any number with an exponent multiplied by that same base with another exponent, this rule is telling us that we can add their exponents. So I would just be able to add those exponents. Do we see that? So an example here is we have 2 to the 4th times 2 to the 3rd power. Well, we have the same base, right? Our base is 2. So we can do what to their exponents? Add them. So we add 4 plus 3, we get 2 to the what power? 2 to the 7th power. Okay? So the long way of working this would be I could do what? I have 2 4s, or 4 2s, right? That's representing this one. And then if I represented this one, I would have what? 3 2s, right? Well, now let's add all those up and you get how many of those? How many 2s is right here? 7, right? So instead of just doing all that, we know we can just add the exponents and we get this answer right here. Does everybody see that? All right.
Would either one be right if you put like 2 to the 4?
All right, so let's do some examples. So A, we have 4 to the 3rd power times 4 to the 5th power. Well, we have the same base. What's our base? 4, right? And so we can do what to their exponents since we're multiplying? Add, and we get what? 4 to the 8th power. Good. Now the instructions here say find each product, but it says to express it using what? Positive exponents. So that tells me I can leave it just like this. Okay? So in your homework there'll be some problems, but they're not asking you to actually evaluate what 4 to the 8th power is. It's just saying express it using these exponents. Okay? All right, so the next problem we have is 6 times 6 to the negative 4th. Okay, well, somebody tell me what, is there an exponent by the 6? Yep, there's always an understood 1, right? Because it's telling me it's that factor 1 time, which is just 6, right? So make sure we put that 1 up there because that's going to help us when we're doing this. So we got to make sure we add what? 1 plus negative 4. That's why we've got to make sure that we have that 1 there. And if we add 1 plus negative 4, we get 6 to the negative 3rd power. But what's our instruction say? Positive exponents. Well, Cameron, how do I make 6 to the negative third have a positive exponent? I'm going to do what?
Take away the negative from the negative 3.
Well, how do I make it a positive exponent? What do I do? Remember what we did yesterday? What do we do when we have a negative exponent? We've got to do what?
Over 1.
We've got to flip it to the denominator, right? And so we're going to get 1 over 6 to the positive third power. We remember that from yesterday? Okay. Good. All right, and then we have our next one. C says 3 to the 4th power times 3 to the 6th power. Reagan, what am I going to do here?
Would you add the 6 to the 4, so it would be 3 to the 10th power?
3 to the 10th power. Good. That would be C. All right, in D, we have 7 to the negative 8th power times 7. Well, the first thing we need to do is what? Put an understood. We need to show that 1 right there so that we don't just think it's not there. So now what's our base, Sarah? 7's our base, right? And then what do we do to our exponent since we're multiplying? So if we add negative 8 plus 1, we're going to have to do what? What are we going to get? So I'm going to get 7 to the negative 7th power, right? Well, again, our instructions say we've got to have positive exponents. So, Luke, how are we going to make 7 to the negative 7th power have a positive exponent? 1 over 7 to the positive 7th power. Good. So that would be our answer right there. All right, y'all are going to work out the next 4 that are on your paper as examples, and I'm going to walk around. All right, so for A, what did we get, Ethan? B to the 4th power. Good. All right, for B, what did we get, Jack?
I got 1 over t to the positive 2nd power.
Good. All right, and then, well, my board says A, but it's C on y'all's paper. Naya, what'd you get for C? Y to the 4th power. Somebody else get something different. Layla, what'd you get? Y to the 5th power. Remember, right here we have y to the 4 times y. There's a 1 right here, right? So we know it's y to the 5th. Remember what we talked about? This is really saying I could represent it like this. And if I count all those up, I'd have 5, right? So that's why we've got to make sure we get our 1 right here because that's another y to it, okay? All right, and then D, our last one. Ollie, what'd you get?
1 over r to the power 6.
Good. That's correct. 1 over r to the 6th power. All right, now we're going to move on to when we are multiplying them when they have a number and a variable together. So here we have 2x to the 3rd power times 8x to the 4th power. Well, what can we do first? We can multiply what? Well, let's multiply the numbers first, right? Because that'd be easier. So what's 8 times 2? We have 16, right? Well, then we have the same base as right here. We both have the base of what? X. So we can do what to their exponent since we're multiplying? Add. So if we add 3 plus 4, we get
7.
So our answer would be 16x to the 7th, right? All right. Now let's talk about something with number 2 because it can be a little tricky. All right. Number 2, we have negative 3n to the negative 9th power multiplied by 2n to the 8th power. All right. So we multiply our numbers, we get what?
6.
Negative 6, right? Then we have what base right here? N, right? So we do what to their exponent since we have the same base and we're multiplying? Add their exponents and we get what? Negative 1. All right. Let's talk about this real quick. If I just gave you n to the negative 1st power and I said represent that using a positive exponent, you tell me to do what? You tell me it's what? 1 over n to the 1st power. You really don't have to write the 1 there, right? Okay. Well, here, what is anything 1 is always multiplied by anything, right? So that's why when we move or we flip our n to the negative first power to the bottom, that 1 stays on top, right? Does everybody see that? So we get 1 on top because when we flip it to the bottom, that 1 stays. But now let's look at this one. This looks like the same exact thing, but instead of it being multiplied by 1, what's being multiplied by? A negative 6, right? Is the negative 6 attached to the negative exponent? No. So it does not need to go anywhere. It does not flip with it unless it's attached to the negative exponent. What's the only thing attached to the exponent? The n, right? So what needs to be flipped to the denominator? The n, right? So I'm going to move the n to the bottom and make it a positive 1, or we know it's an understood one there. And then what's on top? Normally it would be just a 1 if we were doing it right here, but what's left on top right here? Negative 6, right? So our answer could just be written as negative 6 over n, or n to the first power. Does everybody see that? Yes? Okay. All right, y'all are going to work out 3 and 4 on your own. All right, so for number 3, what'd you get, Reagan? 12y to the third power. Good. And for number 4, Luke, what'd you get?
15 over r to the 4th.
What kind of 15?
Negative.
A negative 15 over r to the 4th, right? Good. All right, now we're going to move on to what happens when we are dividing monomials, okay? So when we divide powers with the same base, again, same base is our key. If one of our bases was 3 and we to the second power divided by 5 to the second power, you cannot subtract those exponents, okay? We do this by subtracting their exponents. So when we're dividing, we subtract their exponents. When we're multiplying, what do? Add their exponents. Right? Easy way to think about it is when you do a multiplying sign, which we don't do that much anymore because we're using variables, right? But if I were to write it like this, if I turned this to the left, it would end up being a plus sign, right? And then a dividing symbol is really just a long subtraction symbol. It kind of looks like it, right? So maybe kind of make that little trick kind of help you remember when you're multiplying, we're adding the exponents. When we're dividing, we are subtracting their exponents. Okay? So our example here, we have 3 to the 6th over 3 to the 2nd. Do we have the same base?
Yes.
What's our base? 3. We subtract their exponents. What's 6 minus 2? 4. Good. The same concept whenever we were multiplying. Here, I could represent this as 3 6s on top, and I could represent this as just what? 2 3s? Well, like we did last chapter when we were multiplying, we were able to cancel out or to make those variables equal 1. Do we remember that? We got 3 over 3. That would equal 1, right? We have another 3 over 3. And then how many 3's are we left with? 4, which is the answer we got here. That is why we know we can subtract and get the answer. Okay? Everybody got that? All right. All right, so example A, Christian. We have 8 to the 5th power over 8 to the 3rd power. 8 to the 2nd power, good.
I'm like that.
What's 8 to the 2nd power? What's 8 cubed? 8 squared.
Yeah, Christian, are you like that?
What is it? Evaluate it. What's 8 squared?
8 to 7 Wait. Oh, 64.
64,
Like
good.
that, Christian.
All right, B, Gray, we have C7 over C to the 2nd power. What do you get there?
C to the 5th power.
C to the 5th power, good.
Do it.
You can't. Okay, number 3, now we've got to be careful. All right, hey, listen up. We got to be careful because we have negative exponents now. All right, here, what's our base, Luke? All right. Sarah, what am I going to subtract? What am I subtracting? Negative 2 minus 2. Well, what happens, Avery, when I'm subtracting? I've got to do what?
You have to add them together to get negative 4.
Right, I've got to add a negative, and then this is going to tell me I need to add them because they have the same signs. I'm going to get -4, right?
Okay, do it.
So how are we going to make this represent this using a positive exponent? We'd get 1 over what? 2 to the 4th power. Good. Okay, so now we're using all the different steps. All right, let's talk about, does everybody have this written down? Yes? Okay. We're going to talk about another way you could work this, now that we know both of those. All right. You subtract their exponents. What's a -2 minus 2? If you're at -2 on a number line and you subtract 2, so you go back to, you're at what, Christian?
Oh, not more.
A -4, right? A -2 plus 2 would be 0, but we were subtracting 2 because we're dividing, right? Okay.
Oh.
All right, let's talk about this one real quick. Listen up. So, if I just gave you this right here, 2 to the -2nd power, and you represented that using a positive exponent, so you would flip it to the denominator, right? Right? You would represent that as what? 1 over 2 squared? So, let's look at our problem right here. Our denominator is 2 squared, but let's kind of not think about that for a second. What did we do to make this a positive exponent? We moved it to the denominator, right? So, what we could do here, since we have a negative exponent on top, is I can flip it to the bottom just like we've been doing, right? So I have a 1 on top, and then I flipped this one to the bottom, so I left with a 2 squared multiplied by another 2 squared, because when I flipped it, it made it positive. Do we see that? We're doing the same steps we have been, there's just a different denominator instead of 1. Does that make sense? And then here we would add our exponents because we're multiplying, and we get 1 over 2 to the, what? The 4th power, right? Well, isn't that the same answer we got when we subtracted the exponents?
So them bring my money.
Yes? So I'm just showing y'all that this is the concept too of a way that you get to the right answer as well. All right, and then let's go over D. We have D to the 5th power
BD to the.
over D to the -2nd power. All right. So this is something you're going to be careful with because a lot of you are going to make a careless error and probably do what? What do y'all think a careless error could be? You're going to subtract probably just 5 minus 2, but is that what it's saying? Yep, it's going to be what? D. It's going to be 5 minus a -2. So we're going to end up what? Adding them.
Bro, you cheating.
And we're going to get D to the 7th, right? Okay, well, using the same concept I just talked about being able to flip negative exponents to make them positive, Ollie, what do you think I could do here to flip this -2 exponent and make it positive? What could I do?
What?
Okay, so we've been talking about negative exponents. How would I make... It's at the denominator, so it looks a little different, but how could I make D to the -2nd power? How could I make that 2 positive? I could move it to where? I can move it to the top, right? Hey, listen up. Listen up, Christian. So I can move it to the top and it becomes positive. But that doesn't mean I flip the D to the 5th. I would only flip it to if it was negative. But it was positive, so it stayed up there. And I flipped D to the 2nd to the top to make it positive. And now I just add my exponents, right? And get what? D to the 7th, which is the same answer we got when we subtracted them, right? Does everybody kind of see where that's coming from? I want y'all to understand the concept from both. Are we good? All right. Y'all are going to work E through H. All right. Carson, will you read that for me? Let's talk about this one real quick. So it tells us, it says about how many times as great. So what do we think that's telling us to do? What operation? What kind of expression are we going to need to use?
I don't have a whole sheet.
Multiplying or dividing? Which one y'all think? All right, so let's talk about something real quick. If I were to ask you, you do have that sheet, Christian. I gave you 2 sheets.
It almost says 4-2.
It's the back of that. All right, so if I asked you how many times as great is 12, then 4. So if I said these same instructions, but I said is 12, then 4. How would you figure out how many times greater 12 is than 4? Somebody help me out. Okay, exactly. Why would we use division, Jack?
Because
What are we finding when we divide something? If I divide 12 by 4, I'm figuring out what times 4 equals 12, right? Right? So I divide this and I figure out that 12 is how many times greater than 4? 12 is 3 times greater than 4. Do we all understand that? Okay, so I look at my word problem. We figure out that we're dividing. So in your blank, it should be write a division expression. Okay? That's what we figure out, is that we are dividing. Okay? Now, let's talk about the order, because order and division matters, right? I said how many times is great is 12, then 4. Do we see that pattern? All right, well, let's look at the word problem. How many times is great is Neptune? Then we have this word then again. Then Earth. So what do we think it's going to be? What do y'all think? Neptune?
5 million.
Do y'all think it's going to be Neptune divided by Earth, right? Because it tells us Neptune, then tells us we're dividing. Earth should be on the denominator. Okay? So what is Neptune? All right, and what is Earth? All right, what do we do with when we're dividing? We subtract their exponents, right? And we're going to get what? All right, well, what is 2 to the second power? No, what is it? Evaluate it. It's 4, right? So the answer to our question would be Neptune's diameter is about what? 4 times greater than 4 times great as Earth's diameter. Does that make sense? Okay, y'all are going to work number 6 now, and then we'll be done.